Welcome to Linear Algebra. Today we are going to explore two of the most fundamental concepts in mathematics, rank and row space. Imagine you are an artist with a massive box of paint tubes, but you want to know exactly how many unique primary colors you actually need to mix every possible shade. That is exactly what rank and row space do for data. They help us strip away the redundant fluff and find the true essential information hidden inside a matrix. Let us dive in and see how this works. To understand what these terms mean, let us start with our artist analogy. Why does this matter? Because in real life, data is often highly repetitive. If you have a tube of pure red and a tube of pure blue, you can easily mix them to create purple. Buying a separate tube of purple paint would be completely redundant. In linear algebra, the entire universe of colors you can possibly mix using your available paints is called the row space. The rank is simply the number of essential unique primary colors you actually need to keep in your box to mix all those colors. If you throw away all the redundant tubes, the number of tubes left in your hand is the rank. Now that we have our intuition, let us translate this into mathematics. We start with a matrix, which is just a rectangular grid of numbers. Each horizontal line is a row vector, acting like an arrow pointing in a specific direction in space. When we multiply these row vectors by different numbers and add them together, we create a linear combination. This is the exact mathematical equivalent of mixing our paint colors. The row space is the set of all possible linear combinations of these row vectors. It represents every single point in space you could possibly reach by walking along the directions given by the rows. The rank is the exact number of linearly independent rows that bring brand new, unrepeatable directions. Before we move on, let us see this with a concrete visual example. Look at this three-dimensional space. The red and blue arrows are independent. They point in completely different fundamental directions. And together, they define an entire flat two-dimensional plane. Now look at the green arrow. It is dependent because it is trapped on the exact same flat plane created by the first two arrows. It does not help you reach anywhere new in the three-dimensional space. Therefore, the row space here is just the two-dimensional plane itself. And the rank of this system is exactly 2, because only 2 arrows are actually doing the hard work of defining the space. So, how do we actually find this rank in practice? This brings us to a powerful process called Gaussian elimination. The goal here is to transform our matrix into what is called row echelon form. You can think of this as a simplified, staircase-like pattern where all the redundant rows are systematically turned into zeros. By doing this, we expose the hidden dependencies in the data. The most beautiful and important theorem here is that performing these row operations does not change the underlying row space at all. You are just cleaning up the redundant information without shrinking the geometric world you can reach. This concept of simplifying a matrix relies on a specific mathematical operation. Let us look at the formula for a standard row operation. Conceptually, this comes from the idea that adding a scaled version of one direction to another does not create a new fundamental direction. In this formula, R2 prime is our brand new second row. R2 is the original second row. The letter K is a constant scaling factor, just a regular number. And R1 is the first row. If you increase K, you are simply adding a larger multiple of the first row's direction into the second row. This operation is the engine of Gaussian elimination, allowing us to cancel out redundant numbers and create those necessary zeros. Now that we have our formula, let us apply it to a real problem. We are given a 3 by 3 matrix A, and we need to find its rank by determining how many rows are actually independent. We start with our matrix, which has rows 1, 2, 3, 2, 4, 6, and 1, 3, 5. Our goal is to create zeros in the first column below the top left number. To eliminate the 2 in the second row, we use our row operation formula. We subtract 2 times the first row from the second row. We chose this specific operation because multiplying the first row by 2 perfectly matches the leading value of the second row, allowing them to cancel out. Continuing with our matrix, let us see the result of that first operation. When we subtract 2 times the first row, the entire second row becomes all zeros. This immediately tells us that the original second row was just a redundant copy, a scaled version of the first row. Next, we need to eliminate the 1 at the start of the third row. To do this, we simply subtract the first row from the third row. 1 minus 1 is 0, 3 minus 2 is 1, and 5 minus 3 is 2. This leaves us with a new third row of 0, 1, 2. We are almost done with this matrix. To achieve the proper staircase shape of row echelon form, we need the row of all zeros to be at the very bottom. So we simply swap the second and third rows. Swapping rows does not change the information, it just organizes it neatly. Now we count the number of non-zero rows. There are exactly 2 rows that are not completely zeros. Therefore, the rank of this matrix is 2. Physically, this means the original 3 rows only had enough unique information to map out a flat 2-dimensional plane, not a full 3-dimensional space. Let us look at a slightly different scenario with a rectangular matrix, which we will call matrix B. This matrix has 3 rows and 4 columns, representing 3 vectors living in a 4-dimensional space. We want to find out how many unique directions these vectors actually cover. Looking closely at the first and second rows, we can spot a relationship. To eliminate the negative 2 at the start of the second row, we will add 2 times the first row to the second row. We choose this because adding positive 2 to negative 2 will give us the 0 we need for our staircase pattern. Let us finish simplifying matrix B. When we add 2 times the first row to the second row, every single number cancels out perfectly, leaving a row of complete zeros. Just like before, we swap the second and third rows to push the zeros to the very bottom. This finalizes our row echelon form. Counting the surviving non-zero rows, we see there are exactly 2. This means the rank of matrix B is 2. Even though these vectors have 4 coordinates and live in a 4-dimensional world, they only span a flat 2-dimensional plane within that world. The second row was entirely redundant from the start. Now that we have successfully used row operations to find the rank, let us prove exactly why this works. We need to establish that adding a multiple of one row to another does not change the row space. Suppose we have a row space built from 2 original row vectors, R1 and R2. Any reachable vector V in this space can be written as a linear combination, C1 times R1 plus C2 times R2. Now, we perform our standard row operation, replacing the second row with a new row, R2 prime, which equals R2 plus K times R1. We want to show that this new set of rows can still build the exact same vector V. Let us complete the mathematical reasoning for our proof. We take our row operation equation and rearrange it to solve for the old row, R2. This gives us R2 equals R2 prime minus K times R1. This shows the old row can be recovered from the new row. Next, we substitute this expression back into our very first equation for the vector V. By expanding the terms and grouping the pieces that belong to R1 together, we get a new equation. The terms inside the parentheses are just numbers. This proves that the exact same vector V can be built using only our new set of rows. Because we can still reach every single point, the row space is perfectly preserved. So we have proven that row operations preserve the space. But why do we care about rank in the real world? Understanding rank is incredibly important in fields like computer science and engineering. Think about data compression, like saving a photograph on your phone. An image is just a massive matrix of pixel colors. If the matrix has a low rank, it means many rows are just copies. The computer can throw away the redundant rows, saving massive amounts of storage space without losing the core picture. In robotics, the rank of a control matrix tells engineers how many independent directions a robot arm can move. If the rank drops, the robot loses a degree of freedom and gets stuck in a singularity. We have covered a lot of ground today, so let us reinforce the three most important ideas. First, the row space is the complete geometric world you can build by mixing the rows of a matrix together. Second, the rank is the absolute minimum number of independent rows you need to build that world. Finally, by using row operations to simplify a matrix into a staircase shape, we easily expose the redundant rows as zeros, revealing the true mathematical footprint of the data. You now have a solid understanding of rank and row space. Great job!